My name's Amy Hodler. I am your host. We have our co-host, Dennis Ururian, as well as Mia Wilson. We're going to be monitoring the Q&A questions, which you can write in questions at any time. So with that, I want to introduce Paco Nathan. I was going to say notorious, maybe, I don't know. Well known, sometimes goes by evil mad scientist. So Paco, you halfway deserve that, but is known as the master of master classes, has extensive experience in graphs, machine learning, big data, and just really helping people create solid solutions in the graph and AI space. So with that, Paco, go ahead and share your screen and take it away. We're all looking forward to how to create knowledge graphs from unstructured data.
Fantastic. Thank you very much, Amy and Dennis. I really appreciate the opportunity to present here, and thank you everybody for joining. And great. Can you see my screen all right now? Is that coming through okay?
Yep. Looks great.
Okay, fantastic. The slides are already up online, and I want to say with these slides, I try to err in the direction of providing a lot of resources. So there's a lot of links in them, and in particular, if there's some areas that you want to explore in much more detail, I'm trying to provide links to primary sources and other tutorials or open source projects, etc. So the slides are available here. There's a QR code. It's also at this URL, and we'll post that URL in the chat in a little bit later on. But without further ado, let me get into the talk. This is how to construct knowledge graphs from unstructured data sources. And thank you, Amy, for a kind intro. Just a real quick background. I've been doing this for a number of years. I got started in neural network research, especially neural network hardware developers hardware accelerators back in the late 80s. And then I went off and did network engineering and ended up on being a guinea pig for a little project called AWS. I got involved a lot with cloud computing early on, and with Spark, of course, I did a lot of work with the Apache Spark project when we were going through hypergrowth. On and on. These days, I'm in a company called Sensing, and I work in an area called entity resolution, looking a lot at knowledge graph construction. The talk I'm going to give here is about building up knowledge graphs from unstructured data sources. And I want to give a little preface for that, understanding why we're doing this talk. And the driver is that there's been so much interest in using knowledge graphs, particularly for AI applications downstream, particularly because techniques like GraphRAG have become really popular. So RAG stands for Retrieval Augmented Generation. It's a way of providing a constrained set of, say, facts to an LLM, so that the LLM can then sequence answers based off of the context that you're working in. GraphRAG is a way of focusing what embeddings will be provided to an LLM to be able to go and give some kind of answer back from a prompt. And a really great example, I got to see Michael Hunger and some other friends doing this demo just before they released it. It's really quite good. It's called LLM Graph Builder, and I think they're kind of productizing it now in some other areas, but the code is available up on GitHub. Definitely check it out. But it's a good example of building a graph that you can use then in RAG, constructing a chatbot, or maybe constructing an agent, etc. In this case, point to some Wikipedia pages and start asking questions about them. This is really impressive work. There are popular open source projects in this area, such as Llama Index, Haystack, LangChain, etc. I'm showing a little bit of code from the Llama Index property graph GraphRAG approach. And these are popular. These are great. I will say that these libraries are pretty large, and in production work, a lot of teams probably tend to go and build their own after they get started with some of these libraries. And part of it is there's a concern that I've had. A lot of these libraries are making the assumption that to get the graph part of GraphRAG, they will go out and take some unstructured data sources and automatically build a graph for you, and then make inferences based off of that. And so it's kind of a one size fits all thing, and sort of automatically building a graph, which has some concerns. One of them is there's great research that just came out of Bosch last month, talking about how LLMs aren't particularly good at being adapted to arbitrary domains to be able to do reasoning over semantic relationships. LLMs are really good for understanding the syntax and being adapted to arbitrary domains for that. But to be able to make some kind of consistent reasoning over semantic relationships between concepts, that's really not what they're built for. And that's also what we're seeing with GraphRAG, obviously, is that we're using techniques like retrieval augmented generation to try to provide the right set of facts, try to guide the LLMs in the right directions, basically taking that reasoning step outside. And because of this kind of caution, I think that when you get into some types of work with knowledge graphs, particularly in regulated environments, you run into trouble by having something that's automatically generated. So I work in an area where I work with entity resolution, and like 60% of our customers are in air gap environments. So you can think of government agencies. It might be tax agencies or cyber threat or counterterrorism or law enforcement, things like this. Voter registration is another big one. Catching illegal fishing fleets, things like that. These are regulated environments where you have to be accountable. There's going to be audits. There has to be evidence. There's a lot of consequences for what gets done. And so a point that I want to bring out is that when you're doing work in investigations, there's usually a kind of iterative nature to it. You don't just build a graph all at once automatically using an LLM. Instead, you're probably curating what goes into that graph. You probably have oversight, and you probably also get a lot of the data that's going into the graph. You get it in tranches. When you're doing an investigation, you'll do some work, you'll go out and do some more investigation, bring in some more data, get some better insights. You just keep iterating on that. And I would say that data science in general is much more about investigation than it is, say, about prediction. This is kind of the nature of what we're doing with graph data science is investigation. And so that fits with an idea of, let's take this process of graph construction and unbundle it and really pull it apart. There's a lot of really good reasons why. The big one is you want to have good data quality. And realistically, in most of the graph practices that I worked in production, we needed to blend both structured and unstructured data sources. And this is something that the current generation of open source GraphRAG libraries aren't really doing so well. They really kind of lean more on the unstructured side, but they don't blend in the structured as well. So part of the rationale for doing this talk is like, hey, let's take a look at what are the steps involved. Let's unbundle it. Maybe you need to be more accountable for your knowledge graph solutions. So you need to provide for having domain experts come and do oversight at different steps. Or maybe you just have some other technologies you want to bring in or some existing knowledge graphs you want to leverage. So that's a lot of the rationale for why to do this talk. And I want to present then a kind of generalized architecture. Now, this is approximate. Not every application would have necessarily everything on here. This is kind of the view of the world of what I'm seeing with a lot of system integrators and customers. And the notion is, how do you blend both structured data sources and unstructured data sources when you're building a graph, particularly if that graph is going to be used downstream in some kind of applications where you're going to be wanting to work with, say, a graph database and a vector database together to provide embeddings out to an LLM to use them. Or maybe some other things downstream. Maybe there's some really sophisticated graph analytics doing some network science. But this kind of architecture is where we see the idea is start out with your structured data sources, start out with whatever, if you have taxonomy, ontology, schema, control vocabulary, etc. Start out with that, bring in your structured data sources. And I work in an area where people build graphs using entity resolution to figure out where are the consistent entities across different data sources. How can you sort of tie these together and provide that as a kind of semantic overlay? Basically, take the top half of this diagram to build up the backbone for your graph to really guide what happens downstream. The bottom half of this graph is what we'll do in the talk today and the demo. But the idea is, once you've got the backbone of your graph, now can you go out and grab a lot of unstructured data sources. And looking across the world, there's a lot more unstructured data sources than there are structured. Kind of an 80-20 rule there. But if you've got the backbone structured in your graph already, now can you bring in unstructured data sources, run them through a couple of pipelines. One is text chunking, and then doing embeddings of the text chunks and dropping those in a vector database so you can use them downstream. The other is parsing the text and building out a lexical graph, tying that into your knowledge graph. And then you have these relationships between the text embeddings in your vector database and the different entities and relations in your graph database. That's the game, and there are a lot of ways to go about it. So this is kind of a generalized approach, but I'll walk you through some examples and also some great open source libraries that are leveraging deep learning at these different points. And we'll break out what all the acronyms mean in the different points here. So just to put this in kind of a bullet list, there's really like a few different levels of detail for graphs that we're talking about. It's not all just one graph. And in fact, if you look at GraphRAG today, that's the other talk that I have. If you look at GraphRAG and you look at the definitions of what the different vendors and the different libraries are providing for GraphRAG, graph actually means like 6 different things if you actually read closely. So I want to underscore this point that we're not just talking about one graph, we're actually talking about multiple graphs and being able to look at them in different levels of detail, sort of different granularity, so that they could project up and begin to build a knowledge graph out of other components down below. And better yet, also, you probably want to have some human feedback wherever you have some kind of intermediate step that's inferring results, like here's inferred relations, here's inferred entities, etc. You probably want to have some oversight, and there's some great human in the loop kind of tools. I've been working on a project called Argila, which was recently acquired by Hugging Face. So you can use open source from Hugging Face to do human in loop feedback. But the view of the world is you've got these different levels of detail. So at a very low level, you've got your data sources, and structured might be coming from a data warehouse, some kind of query results, or it might be coming from, say, JSON files, CSV, spreadsheets. And then unstructured sources might be a collection of log files. They might be texts that are scraped from web pages, might be scientific papers, etc., patent applications, all that. But you go up another level and you've got what often gets called a data graph, where you're taking and pulling together on the left-hand side. Your structured data is being organized in a data graph. It's kind of noisy and it has a lot of details. You certainly would not want to use that for inference, but it's like a staging area where you organize your data. It does track a lot of the provenance though. So you can trace back, where does this data come from? But then once you can start to do your linking inside the data graph, then you can promote the entities and relations and properties and whatnot up into your knowledge graph, the thing that you want to use and do inference with. On the right-hand side, going from unstructured sources, then you can build out a lexical graph and tie these into your knowledge graph. So again, I want to try to show the idea here is to be able to take both structured and unstructured, bring them together. In this talk, though, we'll focus on the unstructured part. A kind of rationale here is in this diagram, the y-axis shows going from very general to more specific kinds of labels or semantics. So, you have down in the lower left side, you've got a bunch of dots there. They're not connected. And in the top right, you've got a graph. And the idea is that whatever elements of your graphs that you can pull out of either structured or unstructured sources, on the left-hand side, you can leverage machine learning models, parsers, domain range closure. If you're doing work with semantic graphs, you could be doing some type of inference off the graph, maybe some GraphML. There could be also rule-based consistency measures, but basically moving from something that's very general to something that's more specific. And we'll go through this in detail, but that's the idea, general to specific. On the x-axis, you're also going from uncertainty to more confidence. These are really two different ideas, specificity versus confidence. But on the x-axis, this is where you can actually leverage the uncertainty in your data to focus and prioritize where it is that you get, say, for instance, human feedback. That is an approach called active learning, where you can start to prioritize what parts do you want to iterate on and try to improve data quality. So this diagram is kind of a general rubric for what we'll show with the open source here. And I don't want to go on the structured side of this too much, but I'll provide a couple of tutorials because they're available. And let's just assume this kind of work has been done separately, probably before. So if just briefly talking about where the structured pieces fit in, it was the top half of that diagram I showed before. And there's a couple of tutorials. My colleague, Claire Sullivan, just finished a really awesome tutorial about working with GraphRAG using LangChain. Claire and I have been working with this data set about businesses in the Las Vegas metro area. And we took some open data from post-pandemic. There were PPP loans during the pandemic to keep businesses afloat. There were some businesses that were caught doing some fairly extensive fraud. And in Las Vegas, there were some really egregious examples. So in the open data, you can actually track some of this fraud and see where things may not look quite right. You can also get a lot of other insights about businesses and how they're organized by using a graph. So we've got code out on GitHub. We've got these tutorials showing if you have structured data, how would you build a graph with it? And then how to use, say, GraphRAG downstream. And there's an insight about this. Abhishek Nagaraj at Berkeley Business School had this quote that I really love. Think of data as an imperfect map of the underlying entities. And so really kind of embellishing on that, you could say a collection of data sets is like an imperfect map. You've got some kind of underlying entities in that data, and you might have classes to describe, again, an ontology of these. You've got relationships between the entities, pairwise. We call these edges in a graph. You might have annotations for all the above. We often call these properties. But the game is really identifying the disconnections in the data. That's really the challenge. And so I like this perspective from Abhishek Nagaraj. And I'm not going to go through the entity resolution side of it too much, but there's some great tutorials. I love this one from Esri, finding bad guys on the high seas with data fusion, basically tracking illegal fishing fleets and using both geospatial with knowledge graphs to find graph patterns to track illegal fishing. There's a bunch of other really good examples here of working with the structured data. I'll leave that there, and let's get into what we're doing here with unstructured, the bottom half of the architecture diagram. Let's show how to go from text sources, building out text chunks, text embeddings for those chunks, and then also go out and parse them and construct a lexical graph, run named entity recognition, relation extraction, and then look to, okay, now that we've got this, we can build up our lexical graph. How do we start to link it into some pre-existing knowledge graph? One of the truisms in this field in machine learning is that, unfortunately, when you go out and read a bunch of papers that are being posted on LinkedIn or whatnot, the rate for being able to reproduce the results in those published papers is currently about 3%. Which means that for 97% of the machine learning papers coming out, good luck trying to reproduce the results. And I've been working in this area for a while with a team doing a lot of integration of latest and greatest research and what's showing up on GitHub. And the integration problems, a lot of the implementations that you see coming out of research are just really difficult to try to use. So there's a test that I have that our teams use, whether or not to really include some kind of project. Number one, is it available as a public repo? Does it have a business-friendly license? Has it been maintained recently? Can the code be integrated as a library without using containerization or CLI utilities? That's a big stumbling block, because generally speaking, if it's open source and you have to use a container to run it, it's probably because the dependencies are atrocious. Not to say the containers are bad, but it's like you want to integrate libraries, not containers. Also, is it compatible with other tools you probably want to use? There's a lot of interactions with things like pandas and PyTorch, where sometimes open source projects might not be useful because of that. And the big thing for me is I set a 30-minute limit when I first start to download a project. I want to be able to reproduce their published results within a certain amount of time. And if I go beyond that limit, it's probably not likely that it's going to be useful in production. So that's a criteria. I also want to explain that in this field of where knowledge graph construction meets natural language, working with parsing unstructured sources, there's a lot of acronyms. And I want to break these down because they get conflated a lot. So named entity recognition, NER, is one that you'll hear a lot. A lot of people are probably familiar with that. We'll be using it. But it's about unstructured data. And it's where you have some span of tokens that have been parsed, and they're known to be a noun phrase. And so you want to figure out for each noun phrase, is it a person, place, or thing, right? Does it represent a nationality or a country or a city? Does it represent some organization or a name of a person? Is it a measure of currency, etc.? So working with nouns, and that's a way to extract entity. Relation extraction is where you look at trying to infer relations, edges that have semantic labels between two entities that are co-occurring somewhere nearby each other in the text. Entity resolution is different. That's where you're working with structured data to disambiguate where are the consistent entities across data sets. So I want to underscore NER and ER are completely different things. One is structured, one is unstructured. But then entity linking, EL, is one of the ways that you can take and start to pull these together. So it's kind of a bridge for integrating what you get out of structured entity resolution versus what you get out of unstructured named entity recognition and relation extraction. The other acronym that's going to be important is zero shot. You'll hear us talk about this. This is where you can take some models that have been pre-trained, but at runtime, you can provide them with a context. Say, for instance, what classes of entities do you want to be recognizing? What kinds of semantic relations do you want to be extracting? So zero shot is really useful, and we'll see that with some of the models that we're using. The demos that I've got here are based off of spaCy pipelines. There are alternatives like Flare and Stanford Core and others that are popular, but I'm going to be showing a lot of work with spaCy. And inside of an NLP pipeline with spaCy, there's a few terms you probably want to get familiar with. One of them is segmentation, and that is where you take a text, you split it into sentences, and then you take a sentence and you split it into tokens. And so you end up with a document that's like this stream of tokens, but it could also be segmented into sentences, for instance. Another thing you see is where we call it part of speech tagging. And this is where we'll take each token and label it with what part of speech can we infer by using a language model. And this was some of the original rhyme and reason for having language models, was to be able to do this kind of tagging. Also, there's a process called lemmatization, where we take what we call surface forms and we map those to root forms. So for instance, if the text says children, you could say that the lemma for children, the root is child. If you see the word running, the root for that is the verb to run in English. So lemmatization is how you can get back to kind of normalizing the tokens and what their root forms are. We'll use that. There's another thing called co-reference, and that's where, say, you have pronouns within a text that are making a reference back to some other entity. Resolving them is really useful, really important. I will say that the libraries for co-reference kind of iffy. There are a couple ways to do this in spaCy, but they're mostly experimental, and you do get in some problems with dependencies. There was a great library for doing this called Allen NLP from like 7 or 8 years ago, and Allen NLP is really great to use for co-reference, but it's no longer being supported. I think Stanford Core has some support for co-reference. I'm not going to reference because it is a bit problematic in these pipelines, but I do want to mention it. And if you wanted to take a co-reference recognizer and put it in a container and then have this as like a microservice on the side, that might be a good way to handle it. Overall, we'll be using a lot of transformer models. We won't be using much in terms of LLMs. Actually, transformers tend to work better for this type of work. But you can think of what we're doing with NLP parsing, you can think of it as a kind of enhanced tokenization, because a lot of the work more currently with LLMs, it's using some pretty dumb tokenization. We kind of threw the baby out with the bathwater when people shifted to LLMs. And now people are finding, oh, wait, actually, yeah, let's go back and redo the tokenization in a smarter way. So you see these worlds kind of blending. But just to show, if I take a sentence, now US researchers say they have uncovered a potential link to dementia. you can parse this out. Here with spaCy, we're showing a parse tree. We're also showing how the nouns, such as US and researchers and dementia, these are nouns that are identified, and named entity recognition has labeled these with what class they are. So now we've got some entity extraction out of just this sentence being parsed. There are some really great tools for doing named entity recognition. We'll show these in practice, but I highly recommend a couple. Gliner is from Uchade Zaratiana out of FI group, and I really like using Gliner. It's a zero-shot model for named entity recognition, so it's really adaptable in context. It's based off of bidirectional transformers like BERT. There's also SpanMarker. A friend, Tom Erson, who's now at Hugging Face, did SpanMarker for his thesis, and it's not zero shot, but you can fine tune it, especially for a given context, which is very, very useful. Also very high performance. These are two of the better NER. And the thing about named entity recognition, it's a way to infer the nodes that will go into your graph. So NER is about inferring nodes. Relation extraction, there's a great library. Jack Boylan out of Quantexa did GliRel. It's kind of building on top of Gliner. And the idea is if I've got a couple of entities that I've extracted, let me see what kind of label should I put on an edge between them, if it exists. So if I've got, Bob Smith Jr. is related to Bob Smith Sr., if I've got a sentence saying that, you might have an edge that says related or child of or something like that in between. But there's some other libraries. There's mRebel, there's OpenNRE. There's been a lot of work in relation extraction. It hasn't really caught a lot of traction yet, though, because it is a bit researchy. It definitely needs more work. I like this project from 5 years ago at Tsinghua University in China, but OpenNRE is a highly trainable. It's also got a lot of nice tooling around it. So I've used OpenNRE, and I've got a separate notebook that shows using OpenNRE. This is an area which I think needs a lot of work, and especially needs a lot of work on how to represent smarter tokenization. But overall, relation extraction is about inferring edges. You want to infer edges that you will put into the graph. And then you'll also hear something called entity linking. This is where you're also inferring edges, but you're taking the unstructured data and then linking it into a graph produced by more structured approaches. And so there's a couple different ways about this, different types of entity linking that are available. Certainly there are services like Spotlight coming out of, say, DBpedia, Wikipedia kind of era. There's also a project that's been making the rounds really promising and impressive called Relic. It comes out of Sapienza University in Italy, in Rome. And I like Relic. It's pretty early days, and it is coming out of a research project. So I'm not going to put this into the demo just yet because I think it's a bit problematic. There are much more mature versions of entity linking. Like, for instance, spaCy has its own version of working with a knowledge base and entity linker. And I will say that my colleague, Louis Guiton, we're working together. Louis is building out an entity linking tutorial based on results from entity resolution. And so I will defer the entity linking part to the expert. What Louis is working on there with spaCy. That's a next part of a later talk. Another thing that you're going to hear a lot about is GNNs, graph neural networks. Between like 2019 to about 2022, so much emphasis on research in GNNs. There's a great book by one of the authors of GraphSage. There's a great preprint that's available free online called Graph Representation Learning from William Hamilton, if you want to do a deep dive in this area. For a long time, this was just kind of a research thing. I think even Neo4j sponsored industry analysis to find out where GNNs were being used in production, like around 2023, and they couldn't really find any. But then the next year, Spotify and LinkedIn both popped up, and they have revenue-bearing use cases at scale using GNNs. And the Spotify report, I think, is really super interesting, how they adopted this. But GNNs are another way of inferring nodes, inferring edges. It takes a lot of work, still kind of more on the research side of things. Don't expect to just jump in and use this right away, because it will take a lot of work to adapt for a given use case, but it's very promising. And so this is also an area of being able to infer both nodes and edges. And then another technique we'll show is something called text graphs. And I think this is highly underrepresented, but I've been working with text graphs for a long time. We have a project called PyTextRank that's been around for a number of years. Text graphs go back to like the late 80s with Udo Hahn and Ulrich Reimer. But then Radha Mahasia took it and ran with it for her dissertation in 2004, went into Google, and she's now one of the lead AI professors at UMichigan. But she did the TextRank algorithm, and I've been working on some teams to do implementations of TextRank in Java, Scala, Python, etc. We've got a nice demo for this up on Hugging Face you want to check. But it's a way of inferring edges, but then also ranking the nodes for their significance within a context. So when you're extracting entities from a text, what are the top most important descriptions for that text? Which entities are ranked higher? And we'll use this for our graph construction. And the reason why is that TextRank really draws information recursively from the text by leveraging the sort of graph-like nature of references when we're speaking or writing. And it's a lot more depth than the kind of similarity metrics you'd get with, say, a vector database. Leveraging these kind of graph analytics algorithms gives you a lot more depth than like the shallowness of similarity metrics. And so key relationships can be found that would be missed otherwise. That's why one of the reasons why GraphRAG is better than RAG usually. And I'll go into showing how this is implemented. And so I know that I'll be talking a lot and showing a lot more on the side of property graphs, but they're not completely disjoint. In terms of like RDF or OWL, we could say that as we're extracting an entity, we could say that each node can get like a baseline definition of being a thing, a very general class in W3C. But as we get more and more information, then we can progress from general to specific, from uncertain to confident, and we can start to add more linking into control vocabularies, etc., more specific class definitions or label definitions if you want, if you're in label property graphs. And that's where you leverage name entity recognition and entity resolution together to do that kind of mapping. Edges also can have a baseline of like just saying it's related. That's like the most generic thing you can say in W3C. But again, you can take the results coming out of relation extraction and entity linking and start to map into controlled vocabularies to give you more specific predicate definitions. So you can still be using some of these kind of approaches. And in particular, I think that in knowledge graph construction, it's important to understand if you've built something, how good it is, how can you measure that? There's a couple of ways to use rule-based consistency checks. On the W3C side, there's Shackle using shape constraints. So I can describe conditions that I would expect to see within a graph, how things are being related, or I can show conditions of things that should not occur, and then apply rules and kick out the parts that violate. This is a way of auditing your graph. And another way of doing this also is PSL, probabilistic soft logic, which gets into more of the area of statistical relational learning. So if you've heard of Bayesian nets or causal graphs, probabilistic soft logic is in that realm. But one of the things you can do is put together probabilistic rules to describe relations you'd expect to see between entities in your graph, and then run the rules against your graph. And what's interesting thing is you can get a probabilistic measure for how consistent the graph is overall, and then for each individual entity, what's the likelihood of it. So if there are outliers, you can show them, you can zero in on them and inspect them, maybe you can change them. What's interesting though is if you're building a graph iteratively, think about getting a PSL measure. How consistent is the graph? And then load up a new tranche of data. And does your consistency change? Because if it drops a lot, you've got a problem in that latest tranche of data, and you can start to zero in on the elements that were in that latest tranche of data to figure out where's my data quality problem. So I really like these. These are ways of testing nodes and edges, and I think the testing part goes along with the construction. You have to have unit tests, right? CI/CD kind of things. There is a GitHub repo that has all this code, but for the sake of time, because I really want to do a lot of Q&A too, I will just show some vignettes out of the demo, and then I'll run the demo. So the notebooks really look at parts of this and explore them in detail But the idea is I parameterize my models. I'm using Gliner small v2. I've got some labels that I want to extract for named entity recognition. I've got some labels that I want to use for relation extraction, etc. I'm going to go in, I'm going to build up a spaCy pipeline, and I'm going to add Gliner and glyrel to the pipeline. And then I'm going to start with some text that I just take one chunk of text from this one article about dementia studies. I run spaCy to get a document parsed. And then let's take a look at what came out of the parse. I've got, let's see here, for each sentence, you've got a parse tree, and then showing NER, like for instance here, we see processed red meat, cancer, heart disease, type 2 diabetes, on and on, US, dementia, on and on. So from the parse trees, we want to take those and start linking them together into a lexical graph. And here's some code for being able to go through and build up a text graph kind of representation of how to construct. And then we're going to go and take a look at the named entities that we'd parsed out and overlay those on top of the lexical graph, link them in. Also look at the other noun phrases from our text and link those in. And so we'll build up essentially entity extraction. And you can see that here's processed red meat, here's nuts, here's tofu. And then we're going to go through another step where we take a look at relations. So we use glyrel to say, okay, for the different entities that we've extracted, can we get some sort of relation, some sort of edge connecting them, and label it? So you can see Alzheimer's Association, country of origin, it's based in the US. Great. And now we put this all into a graph and we run a graph algorithm on them. It's for centrality. We measure what are the nodes that are most linked throughout the graph. And you can start to get a rank to say, okay, well, the most important thing being discussed in this article is dementia, which is true. It's about dementia research. And it's about studies in the US looking at the contrast of people eating a lot of processed red meat versus plant source proteins, on and on. So you get this kind of ranked list here of the entities that are being extracted. And here we'll just use PyViz to show what this one chunk of text, what kind of graph it produces. I think it's pretty fun because like the red meat clusters over here with like salami, bologna, bacon, sandwich meat, all the stuff that's really tasty, but leads to this other cluster here of heart disease, cancer, type 2 diabetes, etc., but also has a lot of bearing on the risk of cognitive decline and dementia. And then, you know, over here we've got alternatives, healthier foods, go to like beans, tofu, soy milk, peanut butter. Actually, I eat a lot more plant-based protein these days. And then you have some other clusters that have to do with like the associations doing research, etc. So, you know, you've got this one graph that's already starting to make some sense out of just one text chunk being parsed. Another thing we do is to run clustering on this graph. And if you zoom in, you can see the clusters really make these different parts pop out. And so summarization of those clustering can be really useful. I also want to show, in the interest of time, real quick, here's an example of how to chunk text and make text embeddings and put it into a vector DB. And then here's an example of taking LanceDB and taking those text chunks and querying it. I said, let's show me the chunks that are closest to Alzheimer. And so, you know, here are the vector embeddings showing the distance, etc. Another thing that I showed was using OpenNRE. It doesn't quite fit in with the demo that I was showing, but I want to show examples of it. Taking, again, the same text example and running through and pulling out some different semantic relations like dementia, risk factor, etc. Okay, now let me just show this real quick. Here's a demo. So there's a GitHub repo. We've got some demo code here that I will run. And if the demo gods are with us, it's going to go through and load up the models. And it really only takes just a matter of a couple minutes to run it. Loading up some models. I'm going through some different URLs about articles about dementia research and linkage with processed red meat. And so it's parsing those, it's chunking those, and then building out the graph, and we'll see the results coming out of that. So give this a minute or two to run. It's going to produce our list of entities, and then we'll have a graph. And yeah, there we go. So for the first article, we come out dementia, foods, bacon, and then down here, dementia, processed red meat, Boston. This was from Brigham and Women's University in Boston. And this will produce a few things. It produces a graph for us, which will serialize out as a NorcX JSON graph, but we could load it into Neo4j or Kuzu or other types of graph databases. It also produces the vector.db and LanceDB. So you've got the vectors as the text chunks. It also produces a visualization that we'll look at. But the main thing is I wanted to show performance analysis. I included PyInstrument to do a stochastic call stack analyzer of how long is each component taking. And it's really crazy because when you look at the time that was spent, it's almost all a matter of loading models or serializing out results. The actual crunching for what we did with graph construction and graph analytics was fractional. Loading new entities into LanceDB took some measurable amount of time, but it's still only a fraction. Everything else is a matter of serialization. These open source projects that I'm showing, they don't take a lot of number crunching. I'm just running this on my laptop. It does not require a GPU. If you have it, great. But I just want to add credence to the idea that this can be done without a lot of exotic tooling. Okay, one of the things that this produces is a graph. And so I want to show that. This is a resulting graph out of a few different articles about dementia. And you can load this up as HTML. But again, you kind of see this thing. Here's some research out of like the Boston area, a couple of research studies. Here's like diabetes and cancer cluster, et cetera, on and on. But if you want, you can enable physics and have some fun with it moving around. But PyVis is a great tool for that. You probably want to use something a little bit larger. And let me just wrap up here and go to questions. I want to show a couple of examples in production. ArcGIS knowledge is from Esri. This takes advantage of structured and unstructured data, putting together a graph with geospatial, with video streaming, with satellite telemetry. And here's an example that our team did with Esri to be able to identify illegal fishing fleets and then extract graph patterns and apply those to find other illegal fishing going on around the world. Really super interesting, and there's a case study about it. Another one that I'll point to, the folks at YHOW, I think, are doing this kind of work really well, taking a look at structured and unstructured data, building up graphs, using those to build agents, etc. They have a very good, Tom Smoker and all, they have a very good view of leveraging closed world versus open world hypothesis in the right ways. And overall, this really does speak to the kind of blending of hybrid AI, like symbolic AI and statistical machine learning being put together. I highly recommend a talk by Frank von Harmelen, who describes that in more detail. And we've got some resources if you want to join us. There's a bunch of communities talking about this kind of work. The GraphRAG Discord is fun. Obviously, GraphGeeks, and I've got some Hugging Face collections of papers on this area. Great books. I definitely want to shout out to Thomas and Oscar. They did Knowledge Graph Enhanced RAG. Also Amy's book here on knowledge graphs, etc. And some events coming up. Definitely check out some of the conferences we have in this space. And if you're interested in software engineering for knowledge graphs, we've got that workshop coming up at ISWC. And if you want to get a hold of me, here's where. And from that point, I will stop speaking and let's go to questions.
All right. So, Paco, thank you for that whirlwind. Well, we're getting started with the first question. And before I open up for the raised hands, one of the questions that came in that I thought was interesting is, what do you do if you have more numerical data so that your data is not primarily language?
Yeah, that's interesting. This is one of the reasons I was showing about the Esri work on ArcGIS knowledge. And the thing there that they're leveraging is multimodal embeddings. So they have an embedding model that works for text, like go from a text chunk into a vector database. But then also, you can run that same embedding model on your graph nodes and your graph relations. And so now I can have some graph embeddings. But also you can run it on geospatial data, which gets into kind of answering this. What if you had more numerical data? If you can have some kind of representation and some kind of multimodal embedding, that's an interesting area. And that's how Esri is leveraging this. They call it like geo AI, but how can we stitch together spatial data, maybe from satellites? How can we take images, maybe from satellites or drones or whatever? How can we take video streaming? How can we take knowledge graphs that have more structured kinds of inference and blend it together? How can we take log files that might be more measurements, that kind of thing?
Mohamed was the first one to ask a question, so he should show up here. Mohamed, your video and audio should be available.
Thanks a lot for this informative presentation. I have a question. I have a use case, which is I want to do some sort of literature review where I receive set of unstructured PDF files just for the sake of simplicity, and I want to rank them based on my inquiry. Like I'm looking for knowledge graph and software engineering papers, and I want to rank them based on similarity. What is your advice here and wisdom to handle this kind of cases? I can receive 10,000 results.
Thank you, Mohamed. Great question. And, the previous project I was on before Senzing at Darwin, we were working with BASF, doing exactly this kind of work because they have so many papers about material science coming out, but also patent applications and environmental impact reports and shipping manifests. They have all these PDFs, hundreds of millions of them, that they want to bring together into graphs and do analysis, maybe doing competitive analysis or value chain analysis or win-back strategies, things like that. And so, the idea is you've got PDFs. Can you parse them? There are some better tools these days for parsing PDFs, although it is a very difficult problem. I've done a lot of work with Python libraries in parsing PDFs. And the trouble with PDFs is, of course, is that it's not like linear text. You'll have a chunk of text and you'll have its position on the page, and you have another chunk of text over here, and somehow they tie together, but there's a bunch of recursive callbacks. So parsing PDFs is really the hard part there. But there's some good tools for this. And then once you've got your text out of that, the question is a lot of the information going to be in tables or something that's semi-structured, or is it free text that you can parse? The tables part gets a little more difficult, but there are tools for that. But if you do have the text out of your PDFs, then you can start to do these kind of techniques. Actually, you could adapt this code pretty readily to be doing spaCy pipelines to parse and doing some named entity recognition and building up graphs using this kind of technique. Once you've got those graphs, then most likely the kinds of topics that you're most interested in will be among the things that are being recognized. How do you understand how to rank those? How do you understand those affinities? So you might build up a kind of small ontology describing what you're looking for, and then use that as kind of the backbone that you bring in other parsed texts. And just real quick, I will mention a friend of ours, Vincent Warmerdam, out of Calm Code, has some really great examples for doing exactly this. He has a process that looks at new papers published every day on arXiv, and then looks for particular topics he's interested in and builds up this pipeline to parse them. Vincent used to work on spaCy and he's using spaCy to do that. So we can show that link later on if you want. There's some pretty good tooling.
Awesome. Thank you for answering that question. Steve Kramer, I am attempting to unmute you so you can ask your question. And
I'm actually doing a bunch of research right now, and I'll try to set up separate time with you as well to talk about it. Sort of like looking at the basically all the archive papers and GitHub repos shared by vetted AI experts, and particularly I want to look at sort of the time evolving graph and be able to detect basically a new day's tweets come in. Are there new topics that emerge, or do they map to previous topics? So I was kind of wondering, you made that comment about that PSL approach for looking at consistency. Do you think that could be potentially applied for that?
It could be, although are you asking more about like understanding kind of bumps in like the topic modeling, like trending topics? Is that more the question?
Yeah, right. Mm-hmm.
I was showing PSLs as a way of doing both construction, but also measuring the quality of construction. So I think of it more as like a quality measure. But
Gotcha.
I think for this, I mean, there are some other ways to understand. This gets to a topic that I touched on briefly. Is like when you talk about GraphRAG and you look at the implementations, there's like at least 6 different kinds of definitions of graphs, and literally different graphs that GraphRAG, different approaches are implementing. And so I think what you're asking there is there may be some types of similarity measures that you want to track more closely or provide, have a little bit more weighting emphasis on. And you can leverage that in terms of understanding what's coming in, what's more salient to what you're looking for. Yeah, actually kind of similar to the previous question, but yeah, we can talk about that. Gosh, what you're working on sounds a lot like the rich context project that we had from like 5 years ago. So I'll talk to you more about this.
Yeah, I'll shoot you notes. We can set up time. That'd be great. Thanks, Paco. Appreciate it.
Awesome. Thanks, Steve. Great to see you. Mm-hmm.
Well, thank you. We are going to unmute randomly Raymond, who will be unmuting you here. Allow to talk to video while we're waiting for the mechanism to work there. Paco, there was an interesting question about centrality as a way to refine your results and how you were actually using that.
Yeah, great. So the idea is like personalized PageRank algorithm is a kind of eigenvalue centrality. There's a lot of different flavors of centrality, and you can mix and match, right? You can experiment with this. In the PyTextRank open source project since 2016, we've implemented, I think there have been like 4 different ones. So shout out to Louis Guiton and Ankush Chadler and Tom Harrison and others who've committed on that project. But we do explore using various different types of algorithms there, and how can some be better than others. And usually there's some mixture. The other thing I want to mention is if you do have a pre-existing knowledge graph source, you can import from a source into wherever you're doing your centrality measure and basically amplify your centrality that way. So there's a technique of using a pre-existing knowledge graph as priors, so to speak, which is something you don't see that as much on the graph algorithm side of the world. That's more of kind of like a technique from practice, but highly recommended.
Awesome. Well, thank you. And Raymond, I believe you should be able to speak if you want to go ahead and ask your question. And I'm going to start I'm going to start a poll that I'm just going to leave up for a minute or two about the next talk. So Paco, as you're answering that, people should be able to see a poll.
Yeah, I had a very, very simple question, which is, are the slides available as PDF? Because it doesn't seem like the slide viewer allows that. But follow on just from the last few back and forths, I'd love to see links to these projects that allow us to query from archive papers,
Yeah, while we're talking, I'll try to dig that up, Concode,
That'd be
while we're
cool.
talking. As far as PDFs, yeah, I publish slides usually using a tool that it doesn't provide PDF. We don't actually have PDF in it. But it's a single page web app. So if you load it up in your browser, all of the information is right there. Let me see about, we will definitely dig up that one from Vincent though.
That sounds super useful.
We probably have less than a minute to go. So I think we'll probably have to leave it there for additional questions. And then for those that had questions, how should they best get a hold of you or follow you on LinkedIn so that they can stay in touch with your work?
Well, I think the best way is join GraphGeeks. We have a Discord. So join and we can have much more discussions there. And we may have some study groups and some other projects. So definitely see us there. We'll be posting about the slides and also other recommended projects based off of the questions that come through.
Wonderful. And thank you everyone for voting on what Paco's next presentation should be. And it looks like at the moment, entity linking is winning, but human in the loop is right behind. So
Okay,
maybe
awesome.
there's a series involved here. So again, thank you everybody. Really appreciate the time, the questions, and Paco, all the time you put into this material is really appreciated. I know we could have gone hours. So thank you again.
Thank you, Amy. Thank you, Dennis, and everybody here.